second. I know everyone's so talkative, so don't get crazy, but I am recording this recitation to post it online. Okay. So just give me a minute and we can get started. Okay. Okay, cool. All right, so it looks like Dr. Clayton has posted some more questions for the exam. And the exam, let's see, I just had it up. The exam will be on October 22nd. So we still have a good bit of time, which is nice because we can take all the time to answer these questions. And if you look at them, and if you look at the questions from the first set, you can see that they're actually kind of very similar. And they actually, they touch on a lot of the same things. And that's because these used to be old exams. So back when this class had open-ended exams, this would have been your exam. You would have to, you know, write out everything. So today we're going to talk about edge dislocations and how those give rise to mechanical behaviors and discuss stress strain. So I hope that is agreeable with everyone. Let me just do my hair real quick. Cool. So previously in class and in recitation, we've discussed perfect crystals, right? We've discussed crystals that are ideal. They don't have any significant amounts of defects. We began to talk about point defects a little bit, but another main class of materials is called line defects, or one-dimensional defects, right? So So this is our perfect crystal, and we can see that each atom is bonded to, 4 other atoms, and it exists. It repeats forever, right? By only drawing a little bit. And so this is a perfect crystal. But what happens if we squeeze in another set of atoms here? And now we have some weird bonding going on where this atom exists. It's an extra, we call it an extra half plane of atoms, right? Because we have an extra set of atoms here that aren't bonded to anything below this line. And so this is called an edge dislocation. and it's denoted by this upside down T. So this upside down T says, hey, above this line here, we have an extra set of atoms. And so what happens is, up top here, we have 3 atoms trying to reside in a spot designed for 2 atoms. So these atoms are all being pushed together to fit into this small space, right? So when you're being pushed together, you're in compression. So above the line, we have compressive forces. And then below the line, here we have these 2 atoms, or specifically this atom that's being stretched and pulled, and he's trying to bond to these, is trying to bond here with these friends, but also up here. So to do that, when you're being pulled or when you're stressed, and that in a tensile force, that's a tensile, right? That's a tensile force. So what happens is the introduction of these atoms creates forces above and below it that give rise to a stress state in the material. So while before the stress state was 0, because there was no forces acting on the system, when we introduce these atoms here, this edge dislocation, we introduce compressive forces above it and tensile forces below it. So already we can begin to see that these tensile, these edge dislocations can greatly affect the thermodynamics and the stress state of the crystal. So one of the questions we have is, how can we define the Borger's vector of the edge dislocation? And so the Borger's vector is just a neat tool, a way to quantify the dislocation in some degree. So to quantify the Borger's vector, what we have to do is take a point, we'll use this point, that is outside of this dislocation weight, and we have to make it's called a loop, a Borger's loop around the dislocation. So to do so, we're going to count 3. 1, 2, 3. 3 atoms across. 1, 2, 3. 3 atoms down. 1, 2, 3. And then 3 atoms up. 1, 2, 3. And now if this was a perfect crystal, but if it was a perfect crystal, then we would have started and ended at the same spot, because we went 3 over, 3 down, 3 to the right, left, and 3 up. But because there was this extra half row of atoms here, the start and the end position are not the same. So then this is called the Borger's vector here. So that gap, that difference between the start and the end point is called the Borger's vector. And this is a way we can quantify dislocations, because if we had a dislocation of 2 units of 2 atoms, then the Borger's vector would be bigger. It would be 2, right? So it's a easy way to quantify the magnitude of the dislocation through the Borger's vector. Now it's important to note that for an edge dislocation, the Borger's vector, for an edge dislocation, the Borger's vectors, they're perpendicular to each other. So the edge dislocation goes this way and the Borger's vector goes that way. For a screw dislocation, the Borger's vector and the dislocation are parallel. So for a screw dislocation, that is kind of like what happens when you have that is kind of what happens like when you have 2 rows of atoms and then one starts to twist, right? And now you see the red peeping out from underneath. That's the screw dislocation. So I think posted on Blackboard, there are some videos about them. We don't really talk about screw dislocations that much, mainly just because they're hard to draw, to be perfectly honest, they're hard to draw. And edge dislocations are, it does the job for talking about, the type of properties you want to discuss. So edge dislocations, an extra half plane of atoms, that introduce different stresses into the system. So above the edge dislocation, we have compressive forces as we try to fit 3 atoms in the position of 2. Below the dislocation, we have tensile forces as we stretch these atoms to bond to these new atoms that we introduced. And then the way we quantify an edge dislocation is through this idea of the Burgos vector. So how we do the Burgos vector is we start at a point not on the dislocation line. So we will start here and we just travel a consistent unit of measure around to see where the start and the end of a loop are. If the start and the end reside on the same atom, then it is a perfect crystal in that region. If there's a difference, that difference we call the Burgos vector. And for an edge dislocation, the Burgos vector and the dislocation are perpendicular to each other. But for a screw dislocation, they are parallel. Now, this becomes really important when we start to talk about breaking things, right? When we start to talk about deformation and stress-strain response. So, any questions on the edge dislocation? I think we're pretty good, I hope. Yeah? Okay, cool. So we have this crystal here, right? It's our crystal friend. And now we're going to start to talk about deformation of crystals, and specifically how we break them, because that's all material science is how things break, really. So when we have the atoms here, maybe I'll just take a couple out like this. When I want to break them, right, I can go 2 ways. I can push on the atoms, right, and that's kind of hard to push on them to break because the bonds are, it's harder to push and compress the 2 atoms together because I'm trying to fit these same atoms in the same spot, and the bonds are like, no, I don't want to do this. That there's a repulsive force there. So it's easier to pull them apart and to break them. So in general, how we describe that will say is that materials are not, in general, materials can be called weaker in tensile conditions than compressive conditions. So this is what we're going to discuss now. We're going to discuss tensile strength of materials. So, the atoms have those bond distances, and when we put the atoms significantly far away from each other, we break the bond. But, there's this sweet spot here where we can like stretch the bond a little bit and then it goes back, right? So we stretch the bond, it elongates, but then it returns back to its original position. And it can do that because, bonds are often modeled as springs, right? So you can stretch the bond and it will return. You can compress the bond, it will return. So in that regard, if here we have length, right? And here we have force we apply. 0 is the bond length. 0 is the equilibrium distance, right? The bond length that the bonds normally want to be at. So what that means is that we can apply a little bit of force and tension and stretch the bond, right? And then the bond will stretch. And then when we let go of that, when we stop applying the force, the bond will return back to its original length. So that's all we're saying. And we're saying that works because it's Hooke's law. So atoms can be modeled as Hooke's law. Eventually though, right, like we will pull the bonds so much that they break, right? The bonds will eventually break. So this linear relationship will only go for so long, right? And then at that point, when the linear relationship starts to break down, we will get another type of response that's nonlinear. So it might look something like this. Right, so now there's no longer a linear relationship between the force we apply and the length that the bond stretches to. So Hooke's law no longer applies, and we call this point here the yield stress, or the yield point. Right? So the yield point is interesting because we have a breakdown in this linear behavior, and that implies that something physically is happening to the crystal because the behavior is changing. And in other words, the atoms at this point are behaving very differently or responding to the stress very differently from the atoms in this point. And so what is happening here is now we're starting to break bonds. Now atoms are physically being broke, the bonds are being broken and atoms are moving. And now when we have metals or we have metallic bonds, what do we know about metals? What do we know about metallic atoms? Well, we know that they have a special type of covalent bonding that allows them to share electrons very easily. So if I'm an atom in this point, I break my bonds here, I move to this point, and there's new electrons waiting for me at this point because they're going all over the place. So then I can break bonds at position A, move to position B, and form new bonds. And then I'm happy again because I still have all the electrons that I want. So in that regard, that breaking bonds and making new bonds, that is called plastic deformation. So let's see. Okay. So, and what that looks like . So here's our edge dislocation, right? This is the material in the false state. When we're in this linear domain down here, the bonds are just being stretched and broke. But if we apply a shear force, what will happen is if we apply a shear force to this crystal, then this bond may break, right? And we form with this atom. We get a crystal that looks like this. And this is permanent deformation. Right? This is a permanent deformation that occurs as a result of the shear force. And so then now when we relax that crystal, that we just made, it's not going to revert back to its original length because we've broken bonds and made new bonds. So how that manifests on this graph here is that as soon as we begin to break bonds for new bonds, and now we have relaxed the crystal a little bit, it will shrink back, but not completely to zero. And this change on the x-axis here is the same change in length that we see in the crystal up top. So this becomes really powerful because we can begin to correlate, macroscopic performance to atomic crystal structural changes. Now, this becomes really powerful, but once we start to compare between different elements, it gets confusing because different atomic atoms have different radii. So a change in 2% can be very dramatic for one type of element and not for another type of element. So to account for that, we don't report just in length. We report the change in length over the initial length, right? And we call that strain, sigma. No, epsilon, right? And then same with the force we apply, that can just change with the size of the crystal we're using or the size of the material. So we like to report force per area, or force plus cross-sectional area, which is in pascals, and that is sigma. And that gives rise to the name of this graph, which is called the stress-strain graph. So, am I right, Allie?
Sorry, isn't it sigma force times area? Because pressure is force.
It is stress is a pressure.
Okay, sorry.
It's okay. No, yeah, it's fine. So yeah. Cool. So this is the stress strain response for a metal. And what we see is this yield point here. This point is the point where we stop having this linear behavior. This linear region we call elastic. And this second region here where we have nonlinear behavior, this we call plastic. And plastic deformation is permanent deformation that occurs in the crystal as a result of breaking bonds and making new bonds. Another interesting point we can have will be this point here, which is the ultimate tensile strength, like the ultimate, how strong a material is, like the strongest it will ever be. And then of course here, the failure point. So this point here is when we have the material break apart. We pulled it so much that we actually broke it. So an important unit would be this part here, the failure strain, right? Strain of failure. So there's a lot of information we can get from this graph. Now, I'm going to draw another graph. I'm going to draw another material on the graph, and we're going to discuss it and try to deduce what type of material it is. So for the second sample, we'll have the second sample. So this is sample A, sample B here. What we see is we have a very steep slope of the elastic region, right? So we have a very high yield stress all the way up here, but the plastic region is very small. The plastic region is almost non-existent. So what does that tell us when we compare these two materials? Well, what it's saying first off is that for material B, the slope is higher, meaning more energy is needed to move or stretch the atoms. So these atoms have stronger bonds because more energy is needed to move them. So we can gain information about the mechanical strength of the material by looking at the slope of the elastic lines. And we'll talk about that again later on when we try to quantify these trends a little bit more. And that property is called Young's modulus. So the Young's modulus, or the slope of the line of B, is much higher. So the material, it has stronger bonds. But if we look at the plastic region, it's very small, you know, compared to the plastic region of A, which is very big. So what is that telling us? That's saying that this material can't really break bonds and form new bonds. Material B, once you break a bond in material B, it's probably not going to form a new bond, or if it does, it's only going to do it very minimally. While material A can break bonds and form bonds very easily. In other words, material A, dislocation motion, right, edge dislocation motion, can happen rather easily, while material B, dislocation motion cannot occur very easily. So with that in mind, we can probably say that A is a metal, because we discussed about how edge dislocations move in metals. And B is probably a non-metal, because B is resistant to dislocation motion. And so B probably has a different type of bonding. So we can call B a ceramic, because ceramics have ionic bonding, and ionic bonding is very strong, you know, it's quantized, you know, positive, negative, very strong. But if you break it, it's going to be hard for those bonds to reform someplace else. So just by looking at stress strain performance and response, we can deduce and make a pretty reasonable guess that sample A is a metal and sample B is a ceramic. And then the last type of material we might have might be something that looks like this. This thawed sample C. When the thawed sample C, we have it has a very low slope of the elastic region. So comparatively, less energy is needed to move these atoms to stretch these bonds. So it's weaker than both A and B, but it can have a lot of strain, meaning it's very stretchy, very elastic, very plastic. And what type of materials are very plastic? Polymers, right? Polymers are plastic. And so because of the type of bonding that resides in polymers, a mix of primary and secondary bonding in very unique crystallographic arrangements, we get a material with very low energy to stretch the bonds, but a lot of strain is required to break the bonds. And in that way, this graph becomes very powerful, because if we do a stress strain test, which is actually kind of cool because it's like, right, it makes a lot of noise. You can plot the data and then get a good idea of how your material is classified in terms of how we like to classify bonding. So A is a metal because it has a pretty high slope and a pretty really big plastic region, right? So it has a pretty significant elastic and plastic domain. If you have a mainly elastic domain with no plastic deformation, then you have probably an ionic type material like a ceramic. If you have a low elastic region, a low slope of this line, and a high plastic deformation region, then you're probably a plastic or a polymer. So when we discussed, we compared these materials in terms of the slope of the elastic line. And because we describe atoms in this way as Hooke's law, right? We can say that y is equal to, what's Hooke's law? Let's say k delta x, right? K delta x, right? Yeah, force, right? Yeah. Right, so in this case, the force we have is the sigma, sorry, the stress, right, is equal to constant, we're going to call this constant E for Young's modulus, because that makes perfect sense, right, times the strain. So this constant here is the slope of this line, and Young's modulus is given in pascals, oftentimes probably like megapascals, because stress is in pascals and strain is unitless, right? Strain is length over length, so that doesn't have a unit. So oftentimes the Young's modulus, you will go into a table of different alloys or materials, and they will report the Young's moduli, and that will give you an idea of how strong the bonds are within that system. Let's see. Okay. How does everyone feel about stress strain, dislocation motion? Good. Yeah, thank you, Mike. Cool. So I think with that, I think that's a good place to stop for today, unless anyone has any other questions about this stuff. I know, as I said earlier, we still have a month. We have a month before the first exam. But then after that, you know, the second exam and the third exam, they come pretty quickly after each other. So these topics will be revisited later on for specific examples. So I know the second exam talks a lot about steel, and where we would just plot the different types of steel on this graph. So it's really important that you understand this graph very intuitively and can read it. So if you would like to discuss that more, we can obviously do that. If you have any questions, let me know. Other than that, thank you all for coming. I hope you have a great rest of the week and happy fall. Okay, cool. So bye-bye. Let's see.